Good day everyone who's watching. My name is Andrian Sutarnio from Tarumanegara University on this research called Validation of Numerical Modeling of Cold Form Steel Lip Channel Beam under Non-Uniform Bending with my fellow partners Mr. Prabowo and Mr. Arif Sandjaya. We'll start a little bit of introduction. As we already know, cold form steel has been increasingly used in the structural material in construction due to its high strength to weight ratio and ease of fabrication. However, with that advantage comes its own risk. Cold form steel members are characterized by thin wall section, making them susceptible to instability like buckling, especially local buckling, distortional buckling, and also global buckling. So, in our study, our main focus is to analyze its behavior on non-uniform bending. But unfortunately, until now, there are limited studies on cold form steel member under non-uniform bending, especially for lip channel, because structural response under non-uniform bending can differ substantially due to presence of the moment gradients. Therefore, this study aims to validate a finite element method approach of cold form steel lip channel beams under non-uniform bending using abacus. So this is a big picture of our model using abacus with the consideration of both material and geometric non-linearities to correctly capture the structural behavior or failure. So on our study case, which is numerical modeling under non-uniform bending, we gotta have a real data experiment, and we got it from this journal from Chen and the others from 2021 research. We want to compare their experimental result to our numerical modeling result. From our experimental reference, this is the loading configuration, which is 4-point loading configuration, and we will keep the shear span number 1 or LS1 in this current picture to maintain its fixed length, and we will change the other shear span, which is LS2, to maintain its non-uniform condition, and we will create a gradient moment. From this table shown, we'll use 6 models for our numerical modeling and its material too. Next, from this picture, we would like to explain a little bit of its boundary condition to match the experimental condition. For example, the beam ends, which is BC1 and BC4, were modeled using pin and roll support. The apply loads over here were introduced as concentrated forces at the two loading points. And why is there some kind of separation? Because it is 90mm wide region at the loading and support location to represent the stiffness zone and ensure uniform load transfer. For the analysis procedure, we will begin with 2 stages. First, linear perturbation analysis is to determine the buckling mode, and second is the nonlinear using static risk method to determine the ultimate flexural capacity of the model from its buckling mode. Before we're going to show our results, here's an additional note, which is initial geometric imperfection were incorporated into the numerical model to trigger realistic buckling behavior, and second, eigenvalue buckling analysis was first performed to obtain the characteristic buckling modes. So here's our results. The validation of our proposed numerical model. So in this table, M-test is the fractional capacity from the other experiments, which is from Chen and the others from 2021. And the M finite element analysis is our numerical results. And the last column, M-test divided by M finite element analysis, is to show the comparison between the experimental and the numerical results. The closer it gets to number 1, it means both results are relatively close. From this table shown, the comparison results are the closest in 0.97 and the highest in 1.04. And if we average it, it will be 1.01. That means the results between both methods are close enough. And this is the graphic between experimental and numerical. X-axis is for the mid-moment span deflection, and the y-axis is for the moment. And the graphic shows that these two methods, which is the black one is from the test and the red one is from our numerical approach, are relatively close to each other. Last, we also shown the failure mode between experimental and numerical model. So, for conclusion, between the comparison flexural capacity, the graphic between deflection in the moment, and last is the failure mode, we can summarize several things. The results demonstrate that the proposed modeling approach is capable of capturing the key aspects of flexural behavior. And second, the validated model offers an efficient tool in terms of cost and time. And last, nevertheless, the study is limited by the range of specimen limitations. And that's it for our research. Thank you.